Okay, good morning, everyone, and welcome to the Central Region Guest Speaker Series. Just a reminder that this meeting is being recorded. We won't capture your webcams, but any notes or questions that you pose in chat will be preserved along with the recording. I'm going to turn it over to Andy Just, who will introduce today's speaker.
Yes, thank you, Jenny. And yes, today's speaker is Heather Reeves, and she's from the National Severe Storms Lab. She's been with NSSL here for 15 years. And at NSSL, she leads a research team specializing on weather impacts on the transportation sector. What she really enjoys is developing decision support tools for forecasters and hearing from forecasters on what's important to them and their needs. And I think today's talk is perfect here with the transition that we've made here across much of Central Region and utilizing the precipitation type output from the National Blend of Models. As many of you know, there's a lot of models included in the National Blend of Models for precipitation type, and each one has their own precipitation type algorithm with it. So we've got a lot of P-type algorithms being included, mixed together to get one final probabilistic blend. With that, I'm going to pass it on to Heather.
All right, thanks, Andy. It's my pleasure to talk to you all today about this subject. It's something I've been looking at for about a decade now, is P-type and P-type algorithms in particular, and how this kind of a diagnosis is made. This particular part of my journey has focused on whether or not we can say one algorithm is better than another. That's been kind of a topic lately. There's been a number of people who've been developing new algorithms, and it's obvious, you want it to be good and to perform well, and you also maybe want it to be better than what other people have done. And so I've just asked the question of, can we declare an algorithm as good, and can we declare an algorithm as better? And this journey toward declaring goodness and betterness, as I call it, is actually one that has a lot of problems along the way. And there's a lot of challenges that face an individual who wants to verify their algorithm or to intercompare algorithms. The choice of verification data matters, and we have lots of options out there. There's ASOS, AWOS measures some types. MPing is out there. There's some abilities now being developed to use artificial intelligence based on camera observations, and maybe there's other new types of technology that are being developed that all of these can influence how your algorithm seems to be performing. The choice of verification metric matters. Like, what are you doing to say that your algorithm is good? Is it just Heidecke skill score? Is it Pierce skill score? Is it something else? Because this matters. These can be different. The choice of how you curate the data and what you want to declare as a hit, that also matters. So if you want to use data that's really unambiguous, the P-type is uniform in time and space, and so you trust that this sounding is in fact representative of that P-type, that might give you a different result than if you just used any old data that existed. The rarity of some observation types is another problem. So things like ice pellets, mixes, they're just not observed very often, and so that influences the story. And then last is the choice of input. If you're using model data to drive your algorithm and to verify how it performs, model data has error to it. And radiosondes also have error because they drift. So you might be sampling something that's producing ice pellets, and it might drift over to a part of the cloud where it's more favorable for freezing rain. And so you may not really be capturing a true vertical profile. So lots of challenges, lots of reasons to be careful about claims of goodness and betterness here. But we attack the above challenges in this project here to answer these questions, these pivotal questions of, can goodness and betterness be unambiguously declared? Is it even possible to do it given all of the above? And herein, goodness I define as the absolute measure of how an algorithm performs relative to performance metrics that you derive from a contingency diagram. And betterness is defined as the superior performance of one algorithm relative to another. And in this study, what we're going to do is compare 3 algorithms. The one that's used in the operational HER model, this one is based on mixing ratios and the surface temperature, not the wet bulb temperature, the temperature. Something I call a modified Bourgeois algorithm, which was developed out of WFO Chicago. It's an adaptation of an old one that's part of the original NSEP suite, only taking into account some weaknesses with that. Like in particular, one that's always kind of bothered me is that the original Bourgeois algorithm used a random number generator in ambiguous environments. I always felt like it was kind of comical that was actually implemented operationally. And then one that we've developed here at home called the spectral bin classifier here. So we're just going to intercompare those three. We're verifying them against 5 winter seasons worth of precipitation type observations from the ASOS network. And in one of the experiments I did, I folded in some data from the AWOS just to see what that would do. And then the input data for all of these is the 1-hour HRRR forecast profiles of temperature, humidity, and mixing ratio. Okay, so right out of the gate, let's talk about goodness. Can goodness be unambiguously declared? So this is just for the HRRR. So when it says HP, that's the HRRR, MB is the Bourgeois, and SBC is obviously the SBC. But we're just looking at the HRRR right now, the probability of detection here, the Heidecke scale score here. This thing called the extremal dependence index, you may not have heard of that one. This is a relatively new metric that was specifically designed to account for rare phenomena. So in the contingency diagram, you have true positives, false positives, false negatives, and true negatives. When you're dealing with something like freezing rain and you're comparing yes freezing rain to no freezing rain, you can end up with true negatives that swamp the distribution. I think for this data set that the order of magnitude difference of true negatives for ice pellets was 3 orders of magnitude larger than anything else in the contingency diagram. And this can cause some of your performance metrics to asymptote toward their extrema. So for categories like freezing rain and ice pellets, things like accuracy or false positive rate, these are not very good metrics to use because they don't do anything about the true negatives. They're just used without any kind of accounting for the fact that true negatives can be orders of magnitude bigger than everything else in the contingency diagram. So this new index here is specifically designed to help mitigate that kind of a problem without vanishing to 0. Heidecke scale score actually does mitigate the problem of true negatives, but it has another problem that when the total number of observations gets very small, the total number of true positives, the value of this goes to 0. And so you don't really get anything that tells you one thing is better than another because they're also close to 0. You don't really have anything to help you distinguish betterness in that case. And so this new performance metric does a little bit better job of preserving the integrity of the performance. And then there's the bias, which I'm sure you've all heard of before. So this is how the HRRR algorithm does for all 4 of these metrics. And you can see that for the POD and the Heidecke scale score, these are not good numbers. This, by the way, is just refreezing precipitation. I've done this for all the categories, but for right now, we'll just focus on refreezing precipitation. So that would be ice pellets, freezing rain, or mixes that include one of those 2. So the probability of detection here and the Heidecke scale score for the HRRR algorithm are not very good numbers. We wouldn't be proud of these. The EDI, this extremal dependence index, is okay. It's decent. And then the bias is phenomenal. This is a very good bias. And this is the thing that we're up against. Can we unambiguously declare the goodness of this algorithm? Can we say it's good and everybody would agree it's good? No, clearly we can't. It's good in some regards, not so good in others, not very good at all. So if all you cared about was it producing the phenomena with the right frequency, the HRRR algorithm is actually very, very good. Its bias of nearly 1 is quite remarkable. But if you needed it to be precise in time and place, this POD tells you you're not going to get that. It's a significant weakness of this algorithm. Well, what about betterness? Because you can actually have this kind of distribution of goodness, not good in some ways, great in others. But if you're just trying to be better, all you need to do is be a little bit better. Kind of the proverbial story of you don't need to run faster than the bear, you just need to run faster than the person you're with. You don't have to be really good, you just have to be better than if you want to play that game. So what about betterness? So here's the POD again, the Heidecke, the EDI, and the bias for now all 3 of these algorithms. And when it comes to the probability of detection, the algorithm we have here called SBC is barely better than this the Bourgeois algorithm next to it. When it comes to the Heidecke skill score, again, this is better, but only just barely so compared to the other two. And it's likewise with EDI, this is better, but just barely better. The only one that's significantly better is the bias, or the HER algorithm has a significantly better bias than either of the other two. So can we unambiguously declare that any of these are better than the others? No. The metrics don't agree on which one is better. Sometimes second and third place are confusing too. Here, for example, Heidecke suggests the HER is better than the Bourgeois, but then if you look at the POD, the opposite is true. And so the metrics don't agree, and those leads that do exist, I think, are pretty unconvincing, excepting for the bias. This difference here, this doesn't look very impressive to me, and I'm sure it's not very impressive to you either. So that's just lumping a bunch of categories in together. Typically, when you see p-type algorithms verified, or any kind of validation exercise, it's done by these 4 cardinal classes of rain, snow, freezing rain, and ice pellets, each one independent. And there's room for even more confusion than what we had before. So now you're looking at a table that in the vertical lists the category, so rain, snow, freezing rain, and ice pellets, and in the horizontal now are those different performance metrics, the POD, the bias, Heidecke skill score, and EDI. And if you look here, the HER algorithm, HP, that's what that stands for, has the best POD for rain. But it doesn't have the best POD for all of the categories. The SBC has the best POD down here for ice pellets. So that changes depending on what you're looking at for the category of p-type. One algorithm is not necessarily going to be the best for all of these. And that's also true when you look across the x-axis, that one algorithm isn't necessarily the best for any one category. So SBC may have the best POD for ice pellets, but the Bourgeois algorithm has a better bias. So, so there's not any one clear winner. The best depends on the category: rain, snow, freezing rain, ice pellets, and any. You could break this down into all of the categories and throw them all in there, every single kind of mix and whatnot that you have. It's going to be different depending on how that algorithm is biased and how it performs. And it's also dependent on the metric, because some algorithms are better in some respects and poor in others. Okay, so I did 9 different experiments with different choices of curation and what counts as a hit. So I did some data curation in some cases, like I quality controlled the data set. In the statistics you haven't seen before, I didn't do anything. I just threw the data in there. And in some cases, I tried to quality control it. I tried to thin it out and make it more refined. So in some instances, I looked to see, are the observation and the sounding consistent with one another? And if there's any inconsistency, I just threw it away and didn't put it into the verification data set. In other instances, I thinned it down to places where I was pretty confident there was a contract weather observer on shift at the airport, and only did those and looked to see how did that change the statistics. In some cases, I was really generous with things. Like I just redefined what I counted as a hit. In the original set of statistics, it had to agree with what was observed at the top of the hour and exactly that in order to count as a hit. So if the diagnosis was for freezing rain ice pellets, but only freezing rain was observed, I said that's not a hit, that was a miss. But in one experiment, I actually counted that as a hit to see how did that change the statistics. And a lot of these details are really difficult things to cull out of a paper when you read it. Sometimes the authors are not very transparent about exactly how they've cleaned the data and what they're defining as a hit when they do their statistics. They just throw some numbers at you and say, look how awesome it is. And like, well, it looks great, but how did you, what data did you use and how did you define a hit? These are really important things. So across these 9 experiments, the range of PODs that we had for the HER algorithm, and this is again just refreezing precipitation, we're returning back to just this lump of rain, or excuse me, freezing rain, ice pellets, and mixes that include those. So the POD for these 9 experiments for the HER algorithm ranged from 12 to 39%. That's pretty significant. The Bourgeois has a range of 18 to 58%. So you can see how you might actually really think an algorithm is doing pretty good or really lousy just based on how you handle the data and what you allow yourself to use for verification. And you can see that the biases have a pretty big range, and this big north end of the range is for that methodology where I let anything be a hit as long as one of the constituents agreed it was a hit. And you end up with these terrific biases that are really just, I've never seen anything like it before. And that in turn leads to these very low high-to-key skill scores. There's a lot of work out there that I see at conferences where I suspect, I don't know for a fact because it's not fully disclosed. Like I said, these details are not usually disclosed by investigators, but there's a lot of times where I see somebody show something with pretty good probabilities of detection for these refreezing categories. And that's the high-end PODs are for that generous hit method. And I'm pretty sure that's what they're doing. They're saying, well, it was diagnosing freezing rain ice pellets. Freezing rain was observed close enough. I'm calling it a hit. But the problem is, this is what kind of high-to-key skill score you get when you do that. It's really low. It's really no better than climatology. You might as well not even use the algorithm at that point. You might as well just sort of look at the sounding and say, this is the environment it is. You're really not getting that precision that the algorithm suggests that you have when it's diagnosing something very specific like this certain mix with these certain constituents. So important takeaways right now are that goodness is clearly a function of the methodology of verification. It really can't be fully appreciated unless the exact details of the verification methods are fully disclosed. And this is, like I said, very difficult information to get when you're reading a paper. Sometimes you just don't know what the authors really did. And so you can't really understand those statistics and put them into proper perspective and really gauge whether or not your own algorithm is in the hunt with this one that's coming out in the paper. And an indisputable best was just impossible for me to declare using this data set and these algorithms. I'm not saying that that's forever and always going to be the truth, but I actually do believe that that's forever and always going to be the truth, simply because of the high temporal and spatial variability of p-types, especially in these near 0 degree environments, which is where you need it, where you want it. That I don't know that we can really say with certainty, this one is the best and it's always going to be the best. Now let's look at an event, a specific event, and see how these algorithms interpret a singular event and what that might mean for your decision making. So this case study happened on February 12th, and you're looking at 6 UTC in this upper panel at some MPING observations in the diamonds, and then these big round fat circles are 4 ASOS sites at Rockford, DuPage, Chicago O'Hare, and then Midway. And so at this time, between I-90 and I-88, there's a lot of freezing rain being observed. There's actually freezing rain stretching down south to I-80 as well. But most of what you see, most of the reports are coming in this corridor between I-90 and I-88. So a really important transportation sector for northern Illinois. If we look at a time sequence of the precipitation type at these 4 ASOS sites, this is what it looks like. So at Rockford, it starts out as snow. That's what the blue means. And then it switches to a freezing rain ice pellet mix. That's what the orange is. And then here to freezing rain, which is what the plain red is. And then it kind of wavers back and forth. DuPage is all freezing rain until about 9:30 UTC, and then it goes back and forth between snow and rain. Interestingly enough, these rain observations are probably errant on the part of the sensor, the ASOS sensor. It probably is snow. It's just not able to distinguish the correct, or probably the terminal velocity just makes it look more like rain than snow. Both Chicago and Midway have this period where it's a freezing rain snow mix that switches over around 4Z to plain freezing rain, and then after about 9:30 UTC you get some variation, some stuff switching out. So we see this solid wall of freezing rain, or freezing rain as a mix, falling between about 4 and 9:30 UTC. So for a good 5 hours we have freezing rain falling in this corridor stretching from Rockford to the heart of Chicago. Okay, so here's 2 different forecast lead times, both of them valid at 6 UTC. The top one is the 6-hour forecast, and the bottom is a 1-hour forecast. And then these are sorted with HER all the way on the left, the Bourgeois in the middle, and SBC all the way on the right. And what you will notice, I'm sure right away, is that it doesn't really matter what the lead time is. The figure on the top row looks a whole lot like its corresponding figure on the bottom row. In other words, the lead time is not really making a difference here. We're seeing these experiments, these algorithms exert their personality across the different lead times, all valid at this 6Z time. And so the HER algorithm is diagnosing this green shade here, which happens to be a pellet snow mix. So pellets and snow mixed together is mostly what it's diagnosing in this corridor between I-90 and I-88. The Bourgeois algorithm is doing pretty well. It's got freezing rain here in red, and then this hot pink that's almost looks like red on my screen. That's a freezing rain ice pellet snow mix. So basically, it's putting freezing rain in here. Some of it is in the form of a mix, but it's getting freezing rain where we know freezing rain was observed. And then the SPC is doing something quite similar. It actually, to me, it looks an awful lot like the Bourgeois. Like here's a little dot of blue in the SPC. Here's a little dot of blue in the Bourgeois. So these two are looking a tremendous amount, a lot alike. It's just the SPC doesn't diagnose as much as the Bourgeois does. So it's calling this particular area here, that's green in the Bourgeois, which is a pellet snow mix. The SPC is calling that ice pellets. And then this orange is the freezing rain ice pellet mixed together, and then the red is just plain freezing rain. So both of these, the Bourgeois and the SPC, are doing a pretty good job of recognizing that this should be freezing rain, which in fact it was. So the HER stands out in this case as the oddball, and I have to be honest with you and fair about the HER. I'm not picking on it. It just lost this one battle. But sometimes the HER is the one that's right, and the other two are the ones that are wrong. So it's not like it's always these two are better than this one. Sometimes the story is flip-flopped. Here's time traces, the same kind of a picture as you saw right here, only now predicted. And since I only have data once an hour, these, it's just every hour. I'm assuming it's the same across the whole hour of the model. So the HER has a lot of this blue and this greenish color, that's snow and ice pellets and snow mixed together. So it's turning toward these colder forms of precipitation. The Bourgeois has a lot of this hot pink, red, and orange, which are freezing rain or freezing rain mixed with some other stuff. And so it's definitely diagnosing a little bit heavy on the freezing rain side, comparatively speaking. And then the SPC has this stuff of freezing rain here, and then the plain yellow is just ice pellets by itself. So we're kind of seeing like a Goldilocks thing, a little bit too much toward the very cold. Maybe it's too much freezing rain. Maybe it's just right. I don't know. Like it's just sitting here giving these different stories that are related but somehow slightly different. But the differences, though slight from the research perspective, I think from the decision points perspective, are pretty important. They may lead to entirely different choices on how maybe roads are treated, whether or not you can let certain airports continue operations during this event. So these are subtle differences in the research perspective, but big differences in terms of somebody's bottom line in dollars. Here's the problem: is that these are very ambiguous profiles, and it's been pointed out to me that I probably have a typo in. I've got a couple of these flip-flopped, but we'll just not look at the positions or the indicated locations and just look at the profiles themselves and notice that the elevated warm layers are very conservative, to say the best. They're not very impressive. And then the subfreezing surface layers, they're not very cold either. Usually to get ice nucleation, you need something colder than -6, which is indicated in the rightmost vertical dash line here. So unless you get complete melting in this elevated warm layer, and if you do get complete melting, you won't get refreezing, but if you don't get complete melting, you'll have some ice preserved that'll make its way into the subfreezing layer, and that'll be able to initiate refreezing. There's also this little bit of drying here, which is subtle, but that could scavenge some of those all liquid particles that did fully melt, and that can make a difference in what your p-type ends up being as well. And so lots of subtleties, lots of microphysical details here that none of these algorithms are fully accounting for and able to really entirely appreciate. No algorithm can. It's a level of microphysical detail that's just not plausible to run in real time. But if you look at what's diagnosed, you could easily believe any one of these diagnoses for these profiles. I mean, just taking this one at Rockford, the HER diagnosis snow, and I could be convinced if you told me this is snow, I'd believe it. I'd be okay with that. I'm also okay with the pellet snow diagnosis, and I'm okay with the pellet diagnosis. It really just depends on what's happening to those hydrometeors. How big is that particle size distribution? How quickly are they falling through this melting layer? How heavily rimed might they be? These are all things that are going to control what's falling at the surface. So any one of these diagnoses is perfectly plausible. But there is this clear bias, and the bias that we saw in the event actually translates to this 5-year data set that we looked at. So now what we're looking at are these ambiguous profiles. So these are profiles that have a relatively modest warm layer loft and then a sub-freezing layer that's also modest by comparison, not something that allows for refreezing unless you happen to retain ice through the melting layer. And as I said before, that's really a product of whether or not you have enough melting aloft to allow for that to happen. So here's how these ambiguous profiles are diagnosed by the HER model. 32% of those are diagnosed as snow. Notice these are all ones with an elevated warm layer and a sub-freezing surface layer. So they all have that sort of characteristic shape of something that you would normally think of as a refreezing kind of profile. And it's diagnosing a third of these as just plain snow, and then another 26% as snow and ice pellets mixed together. So it is in fact trending toward these colder p-types. It's not just that one event. It's in general, it does this. The Bourgeois algorithm has about 38% of these actually diagnosed as freezing rain, and then another 13, 8, and 9% diagnosed as some mix that includes freezing rain. And the tendency toward freezing rain is a deliberate choice on the part of the developers who revisited the Bourgeois and the modified Bourgeois, and they purposefully tilted it this way. And then the SBC is clearly biased toward ice pellets, with about 43% of these soundings being diagnosed as ice pellets. The one that's most representative of what actually happened is the Bourgeois algorithm. It's got the best performance metrics for just this set of profiles. But you can see there is some clear bias in these algorithms. And sometimes, like I said, sometimes the HER strikes it lucky and it's the one that got it right, and sometimes it's one of the other two. So it's no one that's better. So now I thought about looking at this from an ensemble perspective, because one of the thoughts that we've had in the community is once you run into ensemble forecasting, you don't need all these different algorithms because you'll have all of the environmental uncertainty expressed, and that will give you the range of solutions that you really need to understand and appreciate what's likely to happen. So these top two rows you've seen before, these are the single deterministic HER forecasts for the HER p-type, the Bourgeois p-type, and the SBC p-type. And this is the 6 and the 1 hour forecast. And then down here in bottom is a 6-hour HER E forecast of the most likely precipitation type using these 3 algorithms. The SBC and the Bourgeois clearly look almost identical to their deterministic counterparts. We're really not seeing the most likely precipitation type being influenced or changed by the fact that we're now dealing with an ensemble. It looks pretty much exactly like the deterministic version. The only one that does look different is the HER, and that's the difference between pellets and snow in the deterministic model versus just plain pellets in the ensemble. So that isn't that big of a difference really when you think about it. I also looked at the probability of freezing rain or freezing rain mix. So this is equal probability. If it's a mix, I'm counting it as the same weighting as if it's just pure freezing rain. And this is what the HER has. It has mostly just one member diagnosing freezing rain across the 9-member distribution. And I know it's only 9 members, so one is hard to say a lot about, but in some of the conversations I've had with forecasters, when it's only one member, they tend to dismiss it and think it's an outlier, it's not reasonable, it's not a solution they need to pay attention to. So in some regards, you might argue that the HER solution here is under-dispersive. It just really depends on what the person who's using it wants to do with it. The bourgeois has really nice, healthy, high probabilities of freezing rain, and the SBC has some elevated probabilities as well. And I got thinking about this. It isn't like we can say the SBC and the bourgeois are better than the HER necessarily. The ambiguous profiles, they really don't occupy a huge fraction of the space. I think I counted up as only 17% of the total number of profiles in the study were something I would consider ambiguous. But sometimes the HER is right. And so it seems to me like there's value in continuing on and looking at all of these and using all of the algorithms and applying them to all of the members, and to have a new axis of uncertainty in the ensemble, something that we didn't have before. And so this is the probability of freezing rain or a freezing rain mix that you get if you were to take a multi-algorithm approach and just weight these 3 algorithms the same as each other and apply them to all 9 members of the ensemble, so effectively increasing our ensemble from 9 to 27 members. And this is now the probability that you get. And these range from roughly from 23 to 67%. So we're getting healthier, higher elevated probabilities, things that are more likely to instigate a response and some sort of messaging. So I started to wonder about using a multi-algorithm approach across the ensemble, across the data as a whole. And so I applied it to the 5-year climatology, because I just don't have a lot of hurry forecasts that I could do this for in any statistically significant way, but I did have that 5 years worth of observations. And so this very confusing slide here shows the rock curve and a performance diagram broken down by rain here in green, snow in blue, freezing rain in red, ice pellets in yellow, and then this refreezing combo of classes here in purple. And the dashed line shows you the probability distribution curve. So probability of 33, 66, or 100% are marked. And those are the only probabilities I have, because I only have the 3 algorithms to play with. But you'll notice that the 66% probability in all of these example seems to be the one that gives us the highest score. I think if I'd had more algorithms, we could have probably gotten these curves sitting a little bit closer into the corners of the diagrams where you want them to be. But whether or not these are better than a single algorithm approach is actually the same answer as we found every other time. Well, it depends. It depends on the category, and it depends on the performance metric. So and it depends on the curation method that you use as well. So here for rain, these darker, more intense colors, these are using the original data set that I used for verification, the original level of curation, just all the ASOS had to agree exactly at the top of the hour. And then I compared it against this method that I've described before called generous hit, where I just let anything that agreed be a hit. Clearly, rain, using a probabilistic methodology, is better whether you're looking at a ROT curve or a performance diagram. But it becomes a lot murkier when you look at some of these other classes, like let's just look at freezing rain. I actually had to go through and do the math, POD minus false positive rate, just to see what's better. Is it the probability here of 66%, or is it this SBC generous hit method, this faded red star? And it works out that the probability method is just barely better, but not in any kind of a convincing way. I really do think there's a lot of promise to continue on down this road going as we go farther along. But the points, I hope, are well taken. Goodness, it's a function of the category and the performance metric, and algorithms can be good in some respects and quite poor in others. Betterness, I don't feel good about saying any one algorithm was better than another. I felt like their apparent superiority was just apparent. It wasn't anything legitimate. It was functionally dependent on the category, the performance metric, and even if it was a slightly higher number, it was usually just by trivial amounts. All of the algorithms have inherent biases that are most pronounced in the ambiguous environments. You really don't see these when you're looking at just general statistics. You don't necessarily recognize that those biases exist. But the biases do emerge even in an ensemble forecast where you're dealing with different degrees of uncertainty and slight variations of those temperature profiles, you still see those biases happening. And they're consequential biases. They can influence decision making. The difference between ice pellets and freezing rain is significant. In a multi-algorithm approach, I really do believe that it can compensate for the unknowns in precipitation evolution and provide that additional access of uncertainty in an ensemble forecast, and that more algorithms might be advantageous as opposed to going down to saying we're just going to use this one. We're just going to use this one and assume, since we're dealing with an ensemble, that we've got it covered. So I think there's room at the table for more seats and influenced by various investigators and novel approaches to diagnosing the phase. I think there's a lot of benefit. I don't think we should be competing to sit in the same chair. I think that we should all be invited to have a seat at this table. And with that, I'll stop and hand it over to Andy.
Thank you so much, Heather, for this excellent talk, digging into p-type and the various algorithms, what's good, what's bad, and obviously that's a very tough challenge to figure out. First, I want to open it up. Any questions out there from those online? In the meantime, I do have just a quick comment. If you really wanted to see why probabilistic is the way to go here for precipitation type, I think this is it. I mean, it's super hard to nail. I think from a deterministic point of view, I've seen through this presentation the challenges we have with verifying, the challenges you have on the research front. Clearly a need here. You're showing blended p-type algorithms, but it also shows that blended models together, kind of like what we are doing in the national blend, is because you're just showing what are things if you just run it off like in a her environment, for example, and what the p-type, but that's just one environment. What if the environment is you got multiple models saying different viewpoints of what that environment would be.
Yeah, I really wanted to run these on multiple models, but the mixing ratios are not archived in the NAM and GFS, so I couldn't run the her. I could run the other two, but I couldn't run the her. So
Gotcha.
So I couldn't look at a multi-model kind of thing, which is something I really wanted to do and still want to do. I think it might be worthwhile in a future iteration of this to just take the SBC and the Bourgeois and partner them with some of the older ones like the Baldwin scheme, the Raymer scheme. And there's also a guy down at the SPC who did a machine learning one. Maybe stick those together and maybe amplify the membership by perturbing the Bourgeois and the SBC, because those are easily perturbed to change their biases, and then create a larger ensemble of algorithms and then see what happens if we do that and what happens if we apply that to different models.
Yeah, I know that Dan Cobb has done some of that kind of stuff too. That kind of concept of just slight perturb, let's just add one C or something to see how much does that that change.
Yeah, and you have to be
environment.
careful. You have to be careful when you're perturbing the algorithms. And this is the problem with the current NSEP, the Unified Post Processor, is that they changed the Baldwin algorithm. They changed one decision point in the Baldwin algorithm, the way that it discriminates between snow and ice pellets, and they kept the original one in there. And so they had that one, they had the revised version of it, so it's NSEP revised. Those are the Baldwin algorithms. And then there's the Raymer and the Bourgeois algorithms, and they were treating these like an ensemble and saying, well, we'll just go with the dominant one, the one that's diagnosed the most. But when you only have 4 members and 2 of them almost always diagnose the same, that you're basically just going to get what the Baldwin scheme diagnoses over and over and over again. So you have to look, you'd be careful when you're perturbing these algorithms that you're actually changing something meaningful about them in a way that's still physically plausible, and not just changing one little decision point that doesn't really change the landscape all that much. Yeah.
Okay. Yeah, any questions out there? All right, no questions. Well, thank you again, Heather, for doing this excellent presentation. I know timing wise, we're coming to the end of winter here, so But I mean, this is all going to be great, you know, kind of review material too as we get into the fall and winter seasons again. So.
Thanks.
All right, and pass it back to Jenny.
Okay, thanks so much, everyone. We will stop the recording and end it for today. Thanks for attending. And if you have any follow-up questions, feel free to reach out. Thanks so much.